Okay, last week we had a real quick, super fast intro on density. That's in chapter 2. We're jumping back to chapter 1 where we left off last time, and we were talking about scientific notation. So we talked about some scientific notation stuff. Remember, that's got the decimal part. It's a number that's got one number in front of the decimal. So doing stuff like way back here, like this 3.5002, we have the 3 in front of the decimal. That's just one number. Perfect. That's our decimal part. We also have the exponent part that shows us how big it is if the exponent is positive, or how small it is if it's a negative exponent. We are going to continue to use that throughout the course. But we've learned some new stuff. So we talked about units last time as well, some of our base units, some of our just like standard boilerplate units. Like if you're talking about how tall you are, you would say feet. But if you're in most of the rest of the world, it's meters instead, because that's the base unit. And it's also conveniently sized close to us. We also have units that are formed from other units. And those are these derived units that we're talking about here on this screen. So many units of volume, the amount of space something takes up, are derived units. If you take a length, like feet, like meters, like centimeters, and you cube it, so if I've got 1 foot in this direction, 1 foot in this direction, and 1 foot in this direction, together that cube would be cubic feet. Feet times feet times feet. And you can do that for any unit of length. So cubic meters is common, especially if you're talking about volumes of air, or like the size of the room. Square feet is good for layouts. Cubic centimeters and cubic millimeters are also units of volume. We also have units that aren't derived units that are volume, and those are liters and milliliters. A liter's similar to a quart. It's not exactly the same, but it's kind of a yard versus a meter sort of similarity. They're pretty close. Another note that will probably come up again later is that cubic centimeters is the same size as a milliliter, is the same size as a cc. Cc just stands for cubic centimeter. That'll probably come up in an example again later. I'm telling you it because it's important potentially for a question. It's also just nice to know. And that is my mom sitting in a 1 cubic meter box at a science museum, I think. Now, to your enemy, your op for this class, significant figures. Some of you will probably be very good at significant figures. You'll get it right away. This will not be an issue. Others of you, this might be a problem for you all semester. I hope that it isn't. For a lot of students, it's pretty common that this is a little bit confusing. We're going to use significant figures all semester just to get you in the habit, in the practice of doing significant figures. It's not particularly scary. There's basically 2 rules. It's just that you have to remember to use these 2 rules anytime we're doing calculations. To get started talking about significant figures. Significant figures, the idea is that we want to make sure that the words, the numbers that we're writing down, that we're saying, are accurate. They reflect the precision of the measurement that we made. If I measured something with a yardstick and it just had 1 yard on it, it didn't have any smaller measurements, and I measured, let's say, the size of my Apple Pencil. How long is my Apple Pencil with this yardstick? I wouldn't be able to make a very good measurement. I would say that it's maybe like, I don't know, a tenth, not a tenth, probably not a tenth, maybe like a fifth of a yard. I wouldn't be able to say that it's 0.457 yards. I can't make that sort of guesstimation. And so significant figures is just reflecting how good of a measurement we made. There are a couple of things that are exempt, sort of, from significant figures. Nickels and anything that comes in whole numbers where you can count them. If I count 1, 2, 3, 4, 5 of my nickels, those are my nickels. I have those nickels at home. 5 nickels. exactly 5 nickels. Nobody in this room, hopefully, would say, no, Mr. K, you're wrong. That's 4.9 nickels. You're lying to us, right? That's exactly 5 nickels. If I count up the number of students in the class, let's say that we've got 59 students in the class. Nobody would say, Mr. K, you're wrong. You have 50.5 students in the class, right? The same thing would work for apples. Apples and other things come in different sizes. If I have 5 apples, I have exactly 5 apples. There's no disputing I have 5 apples, even if one of them is really big, right? So for things like this, it's exactly that amount. This is an exact number, exactly 5. This is sometimes confusing. So that's a situation, it's exact. Other times, it depends on how precisely it was measured. For example, this 250 kilogram, I think it's 250 kilogram, or maybe it's 250 grams? No, 250 kilogram gold bar. This immensely massive gold bar that's real, it exists. It says 999.9. So 0.9999 of that, 99.99% of that is gold. They verified it. Some bank said this is this whatever purity of gold. So you know that there's at least that much gold. You wouldn't be able to say, well, it's 50% gold, right? No, we have the actual measured amount, 99.9%, 99%. And it's 250,000 grams. Huge, giant gold bar. The amount of gold that's in there depends on how good the measurement was, and it was a really good measurement. Another example of measurements. This is data from a couple years ago. Scientists concluded that the average global temperature has risen by 0.7 degrees Celsius since 1880. And that's based on the analysis of records from thousands of temperature measuring stations around the world. So lots and lots of places around the world that have been measuring temperature every day or every so often, right? Making temperature measurements. They take all those records, compile them together. Some nerds do some data on it, some statistics. And they conclude it's 0.7 degrees Celsius, a little bit more than a degree Fahrenheit. If we add zeros to that, it is not the same number. 0.70 degrees Celsius implies a higher degree of precision. That would mean that probably all of those weather stations measured to the 100th of a degree Celsius. Most of the time when we're measuring temperature, it's in single degrees Fahrenheit, or maybe tenths of a degree Fahrenheit. So it's unlikely that they would have that level of precision. If we add more, or if we just use the average value that the computer might have displayed with all of the decimal places after it, this implies that they were making very, very highly precise measurements of temperature at all thousands of temperature stations around the globe, which seems incredibly unlikely to me. I think very few people are measuring their temperature to that level of precision. Overwhelmingly precise. Number or measurement. And so it would be misleading or inaccurate if we were to use that number instead of the 0.7 degrees Celsius. So what we're doing with significant figures is making sure that we're keeping track, kind of loosely, of how precise are measurements. If we made good measurements, we'll have more significant figures, more digits. If we had very imprecise measurements, we'll have fewer numbers. This is a rough generalization, but generally, the more precise our measurements, the more numbers that we get to include in our measurement. And this is something that scientists all over the world do, and intro Gen Chem students like yourselves all over the world are also learning. Within every number, every measurement, except for the number of students in the class, the number of nickels on the bookshelf in my office, the number of apples that I ate before coming to work, right? Those things are exact. For everything else, there's uncertainty. There's a little bit of plus or minus. That's what the uncertainty is. And that's baked into the last digit. The very last digit, there's a little plus or minus on that. We might be a little bit over. We might be a little bit under. More likely than not, we are one or the other. So there's a little plus minus built in or baked into it. That's where all of our uncertainty lives. And we'll see examples of that when I show you some measurements. Okay, so like that last bullet point, our numbers, our scientific numbers, get reported so that every digit is certain, except for the last one, which is estimated. So let's say that we have this number. Somebody just provided this 45.872 number to us. The first 4 digits, we are absolutely certain these are the correct values. This 2 could be a 3, maybe. Could be a little closer to 3, could be a little closer to 1. There's a little bit of wiggle room there. We're not 100% sure that it's exactly 2. It's probably not exactly 2. So a little bit of plus or minus in there. An example of how we would see this making a measurement. Here's a nickel and a little digital ruler in centimeters. This nickel, we would look at our ruler. Conveniently, I've got these lines on here, right? So we can see it's lined up on the left side of the nickel at the 0. And so we would read out then to this red line. And this red line is past the 2. It's definitely past the 2. Nobody would argue that it's not past the 2. And we have subdivisions on our ruler. So we've got tenths. That's these little tiny tick marks, as well as the half mark. So this tick mark would be 2.5 centimeters. And we are just past the 2.1 centimeter mark, right? We're definitely past the 2.1 centimeter mark. We can see that we're past it. And we are not to the 2.2 centimeter mark. However, if we say, let's magic, zoom in, enhance. If we zoom in, right, it would also be misleading. It would not be quite accurate to say that we are at 2.1. Right? We're a little past the 2.1. We're not at the 2.2. We couldn't say that either. We're somewhere in between. And so we get to guess. We get to make our best guess, our best educated guess. What do we think that looks like? So the way that we do this, typically, we're going to, in our minds, break that up into roughly 10 subdivisions. And just kind of on vibes, how far past 2.1 is it on the way to 2.2? Who's got a guess?
About 4.
4? Not quite to half, right? You might look at it and you might see, oh, it's at the half. Maybe it's a little before the half. I would say that it's definitely not past the half. So 2.1, and then we're guessing on this next decimal place. So 2.1, and this is where the uncertainty comes into the measurement. You might say 3, 4, or 5 centimeters. Those would all be fine measurements. It's important that you make this estimate. In our labs, we are going to be doing analog measurements like this. It's important that you make these little estimates when we're doing measurements. They're worth points. So that's one way to incentivize you and prove to you that they're important, because they're important to me. Questions so far? All right. Another example of doing this measurement, I tried to find, I went out and found this image, and this was one of the few where they actually were wearing socks. I thought dogs on the timeline was not the right choice. So, right, if we zoom into the scale, we've got our 115, that's this long mark. (115 kilograms). We are just past 117 kilograms. And to my eye, we're just barely past it. So I put a measurement of 117.2. Sometimes students will go a step further. They would say 117.20. I cannot, between these two little tick marks that are maybe a little hard for you to see, I cannot, in my mind, create 100 subdivisions between those two tick marks. So that's why we only go to one place. Pretty much everyone can probably break it down into tenths. Hundredths is beyond me. I'm guessing it's also beyond you. So the estimate is just one extra digit. Not two, not three, just one. And this is only for analog measurements. If it's a digital measurement, like the balances that we have in lab, it's just the numbers that the scale says. It's already baking in that uncertainty, so you just write what it says and then no more. Another example of a different type of analog measurement. This is a 4-beam balance with a brick on it, an indestructible object, a Nokia phone. This scale has markings every 0.01 grams. So the way that you read this scale, you just add up the numbers on each of these 4 beams. So we've got 100, 30, 0, so 130, and then we've got this little thing that's super blurry, this little guy. That's our last couple of place values. So it is past the 0.5. It looks like, to me, it's right on the 1 mark past the 0.5, so that'd be 0.51. And that 0 is our estimate. So even if it looks like it's spot on, like in this case, it looks like, to me, it's spot on this 0.51, we still need to show that we estimated that it was right on. And so that's when the 0 comes in. This is the most forgotten estimate number. Lots of times people will just leave the 0 off. We do have to include it. It makes a difference. You might also not think that it's right on the 0.51. You might think it's a little over. You might think it's a little under. That is fine as well. I will encourage you to fight with your neighbors in lab about what your estimates are, lightheartedly, of course. It's really not that important. It's just important that you make the measurement. OK, let's say that it's winter. Conveniently, it is winter. And you're staying up at a cabin in the mountains, and you want to figure out how many layers you need to put on, or how cold you're going to be if you go outside. You have this outdoor thermometer that you can see from inside the cabin, from the safety, from the warmth. And it looks like what we see here. For practice, record that temperature reading to the correct number of digits, and remember to include units. There's a zoom in for you. it may be helpful to think about we're definitely past and we're not past, to kind of frame where we are with our number and then do your estimate between those two numbers. You're welcome to compare with your neighbor as well. Do we have a brave soul who would like to volunteer a number? That was very fast. Yes?
I'd say negative 8.2 degrees Celsius.
We've got a vote for negative 8.2. Any other guesses?
Pretty good guess.
Yes.
Negative 7.7.
We've got a guess for negative 7.7. Any other guessers? Yes?
Negative 7.8.
Negative 7.8. An encouragement, an admonishment. We're in a classroom setting. What are you here to do? Learn. You're not here to be an expert. I'm here to be the expert and to help you learn. If you make mistakes in the classroom, this is the place to make mistakes. This is the place to have wrong answers, and giving a wrong answer, writing down a wrong answer, committing to a wrong answer, and then finding out you were wrong produces a good stimulus for you to remember, oh yeah, I made that mistake that one time in class. That will help you learn. Writing down an answer, participating in some way, even if you don't say it to anyone, even if you don't volunteer, that helps you learn. So please keep doing that, and thank you everyone for your volunteers. I see that you want to change it.
Yeah. I was going to change mine to negative 7.8 now.
Okay, we've got the minus 8.2 has decided 7.8 is better. So our 0, right? This is 0. This is negative 10. So we are counting. We're increasing in magnitude. The size of the number is increasing as we move to the left. We've got our minus 5, 6, and then minus 7. So we are between minus 7 and minus 8. And we appended or amended that number. So we're between our minus 7 and our minus 8. I would say that we are past halfway, and we've got some disagreement about exactly how far past halfway we are. We're closer to the 8 side, so this might be a 7.7, 7.8. You might even say 7.6. Those are all perfectly fine answers. Not z, minus 7.8. And each of these should have degrees Celsius, since that's our unit. Questions? Cool. All right. So that's an introduction to making measurements. Now on to the real fun part of it, significant figures, counting out how many significant figures we have. There are some rules for significant figures. We're going to have lots of little lists of rules like this throughout the class. Chemistry has a lot of details, and my theory is that's part of what makes it very difficult for students. There's a lot of little details to remember. So for significant figures, all of our non-zero digits are significant, all of them, all non-zero digits. If it's not 0, it's always significant. So that includes the 1s and the 5s in these examples. Those are all of our non-zero digits. Now on to the zeros. Interior zeros, if they're between two numbers, those are significant. So all of these zeros are significant. And significant figures is often shortened as sig figs, and also further shortened as SF. Other zeros that are important are trailing zeros. with this fun caveat, if there's a written decimal point. So anytime there's a decimal point shown, our trailing zeros, zeros to the right, are all significant. So all those zeros are significant. And the non-zero digits are still significant. Short pause for people to write. And we remove our pause and we get on with making biscuits. Trailing zeros before an implied, not written decimal point are ambiguous. May or may not be significant. It's kind of just question marks. So these zeros might all be significant. It might be that none of them are significant. Could be that in the case of 50,000, it might be that 2 of them are significant. The way that they're written out currently, it's not clear. An example, 350, 350, could be 2 significant figures. It could not be 1 significant figure. It's definitely at least 2 because we've got 2 non-zero numbers. So 2 non-zero numbers. The 0 might be significant. This is a case where we would want to write it in scientific notation. If we write it as 3.5 times 10 to the 2, it's 2 significant figures. Notice we didn't write a 0 after the 5. Trailing zeros after a written decimal point are significant. We didn't write one. We just have the non-zero numbers, 2 significant figures. If we write it as 3.50, we've added that trailing 0. We've got a written decimal point, so it's significant. These situations are likely to happen at least once during the course of our labs, where you'll get a number like 350 or you'll get a number like 40, and you have to reflect how many significant figures you have, so you'll have to switch it up into scientific notation. Another case of zeros that may or may not be significant, in this case they're not, is leading zeros. If we've got zeros to the left, they are not significant. They're just showing us where the decimal point is. So if we wanted to, we could rewrite these in scientific notation, and hopefully you would write them like this. We would not write them as, for example, 0.00005 times 10 to the minus 4, right? That looks silly. Same thing for the 0.0153. Do we have questions about any of those rules? We will have some practice for you to try them. All right, we also have exact numbers. We talked about exact numbers a little bit before. That was the nickels, the 5 nickels, the however many students I said that we had, the number of apples. Those are exact numbers. And so the way that we treat those in significant figures is that they have an unlimited number of significant figures. This will be important later when we have to consider how many significant figures different numbers have. We have exact counting of discrete objects, countable whole objects. For example, we will have an example of this. This will show up in one of our labs. I think it's next week's. Integral numbers that are part of an equation, like 2 in d equals 2r. Diameter is twice the radius. When we're talking about circles, that 2, for example, that's an exact number. And some defined quantities, like 2.54 centimeters equals 1 inch. That one hasn't always been exact, but they changed it, I think, before my lifetime. And that is now an exact one. That's one of my favorite conversion factors. Other conversion factors, all scientific, not scientific, all, what's the word I'm looking for? SI unit prefixes. Like kilo and nano. All of those are also exact. So like 1 kilometer equals 1,000 meters. That's an exact conversion. All right, we've got a bunch of numbers here. Determine the number of significant figures in a number. As a reminder, we've got non-zero numbers. Those are always significant. So things like 2 and 5 and 1. We had the interior zeros, things that are in between two non-zero numbers. Those are also significant. Trailing zeros after a written decimal point, after all of our non-zero numbers, those are significant. The leading ones, the ones in front, are not significant. I'll give you just a little bit of time to look at these, and I'm going to go over them as well. All right, as promised, that was a little bit of time. How many significant figures do we have in each number? In A, we have 3 non-zero numbers. So 3 significant figures. Nice and easy. In B, we have 2 non-zero numbers and leading zeros don't count or aren't significant. So that's 2 significant figures. Letter C, 52.90. We have 3 non-zero numbers, 3 New Zealand, and we've got a trailing zero. With a decimal point. You don't have to write out the full explanation. I'm just doing that so if you look back at the notes, there's an explanation there instead of having to go back and watch the recording. So 3 plus 1, 4 significant figures. Once you get good at significant figures, if you really get it down, it's pretty much instantaneous. It does take practice. All right, letter D, we've got our 2 non-zeros. We've also got 2 interior zeros. And the 2 leading zeros don't count. So this one is 4 significant figures. How many significant figures do we have on E? I've heard two different options. Well, three different options. I've heard 1 and 3. Could also be 2. I did hear a 1, 2, 3. So this one, it's definitely 1. But it could also have more. The zeros are ambiguous. So if this was a measurement that we made, we would want to think, okay, what did we use to get that measurement, and how many significant figures should it have based on what we used to get the measurement? So this is 1, 2, or 3 significant figures. That's something that we would want to try to avoid. And how about F, 6 atoms? How many significant figures does that 6 have? Just like the emperor's power, unlimited. Exactly 6 atoms. Atoms are countable. Even if it's really hard to count them sometimes, you can count them. So if you were able to count 6 atoms, unlimited significant figures. Questions about any of those? If you have questions or confusion, it'd be a great time to sort those out as soon as possible. All right, we continue. If you can believe it, that's the sort of easier part. We are also going to be using significant figures in calculations. And so the result will be rounded. Because oftentimes you plug stuff into your calculator and you get 8 digits out the back end of your decimal place. Right, your calculator might give you that result. And so we would need to round that number off to reflect the number of significant figures in our calculation. If we have multiple steps, we want to round only the final answer. This is because if you do a rounding, right, like if we round this 4.56 to 4.6, we've added 0.04. We've made a little change to it. If we multiply that by something, that 0.04 can start to build up if we do a couple of steps of multiplication or other steps. We'll see this show up in the labs, probably. So if we only round the final answer and we don't round off between steps, that will save us from making those rounding errors. And that's more points in your pocket for your grade for the class. In labs, every number that goes into a data table should have the correct number of significant figures. All right, so for making measurements, these numbers will have been rounded. If we go on to use these numbers again, and these were rounded numbers, we need to use the unrounded numbers. So it may be helpful, for example, let's say this was 4.45. We would use the 4.45 in calculations. And in classic me fashion, I've written off the edge of the paper. the calculator that I like for the class, the one that I've mentioned, this one, the TI-36X Pro, my favorite scientific calculator. This one's great, partly because you can go back to previous answers, highlight it, press enter, it pulls the whole number out. You don't have to sit there typing in all the numbers and making sure that you put it in correctly. You can pull things back from previous problems, which is really helpful when we're doing stuff like this. I'm sure that Casio has a thing that does that as well, and it's probably cheaper and does just as good a job as the Texas Instruments one. I'm just hooked on Texas Instruments. I'm also hooked on phonics, which is a joke that most of you probably didn't get because you're not old enough to have remembered. Anyway, so that's one of our tricks. When we are rounding things, our rules for rounding, in case you haven't rounded in a while, let's say that we want to round 3.74 and 3.76 to two significant figures. If the number, the first number that we're cutting off, is 4 or less, we just drop it. So this would become 3.7. I don't remember if I include this later in the slides. That 3.76, 6 is 5 or higher or bigger, and so it would be 3.8. Just in case it's been a while since you've rounded things. When we are doing multiplication and division with significant figures, the result, what we get out of our multiplication, our division, gets the same number of significant figures as the factor with the fewest, the smallest number of significant figures. So for example, we've got 5.02. We have an interior 0, 5 and 2 are non-zero. We've got 3 significant figures. 89.665 are all non-zero, so we have 5 significant figures. 0.10. We have a leading 0. That doesn't count for significant figures. So we've got 3, 5, and 2 significant figures. The smallest of these being the 2. And so our product also has to have 2 significant figures. The way that I will usually notate what our last significant figure is with a little line under it. So I'll put a little line under this 5, and then an arrow pointing at the 0. That's the one we're looking at to see if we round. We don't care about any of the other numbers. And since 0 is 4 or smaller, we round this down to 45. The reason that I do the little line underneath is when it's words. The little line underneath is helpful if we have another step after this, right? We're reporting the 45 maybe in one of our lab data tables, but we're going to use the number again for a calculation so that we don't have to go back to our initial calculation, figure out 2 sig figs, and then it's the 5. This lets us look at the number and we immediately know what the last significant figure is so that we can use it again in future calculations. So it's just a little note-taking method. If that works for you, if you like it, you're welcome to use it. You can use something else, or you can ignore it altogether. But that's the method that I like. And then for this division example, 4 non-zero numbers, 2 non-zeros plus a trailing 0. So we've got 4 sig figs and 3 sig figs, respectively. 4 is smaller than 3. So again, this 5 line means it is our last significant figure. An arrow at the 9. Arrow means this is the number we look at. Could have written this shorter. For rounding. So rounding this off to 3 significant figures, 0.966. Questions about either of those? When we're writing things out that have a decimal, things that are smaller than 1, please write the 0 in front. It's not critical that you write the 0 in front, but it is helpful for letting us know that there's a decimal there. If you miss that there's a decimal there, suddenly you might be putting in 966 instead of 0.966. And those are going to get you very different numbers. If you come and check your lab with me, I might be able to catch that for you. But if you can catch it for yourself, that's better, because I'm not going to be checking your work when you're working on an exam, for example. So good to include that. Good, I do have a slide about rounding. Here it is again. So a couple of examples. We're rounding all of these for 2 significant figures. We start from the left, so 2.3, 2.37, 198.67. The underlined ones, that's our last significant figure. We look at the next thing to see how we round. 198.6. The 9, if you add 1 to 9, turns into a 10. So then this suddenly becomes 200. But again, we only have 2 significant figures, and so we need to put it in scientific notation. To be correct. If you just write 200 there, you're losing at least half a point. Half a point is the typical penalty for wrong significant figures per occurrence, up to a limit. All right, more examples. We want to do these calculations to the correct number of significant figures. How many significant figures does our first number have?
5.
It's 5. We've got 4 non-zero numbers and an interior 0. Those are significant. And how about 90.300?
5.
Also 5. We've got 9 and 3 that are both non-zero. We have an interior 0, and we have 2 trailing zeros with the decimal place written. So these are also significant. So we plug that into our calculator. Calculator says this. That's everything the calculator has on it. So we write the whole thing out. We round for 5 significant figures. The second 5 is our 5th digit. Look at the 6. Are we going to round up or down? Up. So 2085.6, final answer. In B, we have 3 significant figures and 4 significant figures. We've got the written decimal point, so all of these zeros are significant since they're trailing. Is our answer going to have 3 significant figures or 4 significant figures after we round it? 3, we pick the smaller one. So 125 times 9. Calculator says 1,125. The 2 is our 3rd significant figure. We look at the 5. 5 is 5 or greater, so we're going to round up. And 1130. Questions? Can you say the last part of that question?
I said, did you have to put the 0, or can you just put the thousand there? Like just the 113, or does the 0 have to be included with it?
We need the 0 because it shows us how big our number is, right? If we write 113, that's 113. We have 1,130. Other questions? How many significant figures does what I wrote have? 3 or 4. We've got a 0. I didn't write a decimal place. It's a little ambiguous. So we would need to write this in scientific notation. So we would write that as 1.13 times 10 to the 3 and that would be our final answer. So that's one of our rules for significant figures in calculations. We also have our other set of operators, addition and subtraction. The rule is different. So in addition and subtraction, we are looking at decimal places or place value. Usually it's after the decimal place. Sometimes it shows up before the decimal place. So the least precise, the one with the least numbers after the 0, that's the number of places that we're going to round to. So 5.74 has how many places after the decimal? 2 numbers, 2 places. .823 has how many? 3. So 3 Dr. Peppers, decimal places. And if we set our calculations up like this, an easy way that we can figure these out, you just run a line down. And that line I've placed after the 4 in our 5.74. That means we'll cut off anything that's to the right. So rounding this to 2 decimal places, 2.65. We look at the 1 to see how we round. Oh, sorry, that's also included. We don't look at that. We put in our calculator. Calculator says 9.214. We round that to 2 decimal places. The 4 says, drop me. So 9.21. we'll do the same thing for our other example. 1 decimal place smaller than 3 decimal places, so our answer will have 1 decimal place. We do 4.8 minus 3.965, 0.835. We round at that 8. The 3 says, drop me. So 0.8 is our answer there. One of the weird things that can happen with addition and subtraction is that the number of significant figures can change, like we saw in that second problem. Here's a bigger example of that. If we look at significant figures, that's not what's important to this calculation, but if we look at significant figures, right, both of those have 4 significant figures. Good stuff. They also have 2 decimal places, and that's what we care about because we're doing addition subtraction. So we're going to have 2 decimal places in our final answer. Ask your calculator, and it'll tell you this is 0.03. That's 2 decimal places. And how many significant figures is it? Just 1 significant figure. So sometimes we can gain or lose sig figs when we do addition subtraction.
So would you put that answer in scientific notation?
You don't have to put it in scientific notation because it's leading zeros. The leading zeros are never significant. It's just for the case of the trailing zeros if there's no written decimal point that we have to put it in scientific notation. You are welcome to put that in scientific notation, though. All right, we've got a couple of calculations. I'll put them in my calculator so that you don't have to. Calculator says 921.996. We need to know how to round this. We have to look at the numbers that went into it. In a lab, these might be numbers that we measured. What do we care about when we're doing addition and subtraction? Decimal places. And we have how many decimal places in this first number? 2 decimal places. And the second number has 3 decimal places. We're going to pick the smaller. So that 9 is our last significant figure. We look at the 6 to see how we round. 6 says, round up, king. And this confusingly, mysteriously, to some of you maybe, turns into 922.00. This later 9 turns into a 10, turns this other 9 into a 10, turns this 1 into a 2. But we keep those 2 decimal places as zeros, so 922.00. And for this other example, we've got what I might call 0 decimal places, and 0 decimal places, and 2 decimal places. Calculator says this is 1990.06. we round off at the ones place. The 0 says drop me. So we get 1990. And again, we're in a little bit of a sticky situation. We know, because we did the calculation, that this 0 is significant, but it's also trailing. There's two ways that we can resolve this issue so that we know for sure that it's significant. One of them, arguably the easier one, just add a decimal point. Now the 0 is significant. This works if we had two zeros and only one of them was significant. We cannot use this option here. In this case, our 0, all the zeros that are trailing are significant. We can use this option, just write a decimal place. Our other option is scientific notation. 1.990 times 10 to the 3. Those are the same number, showing the same number of significant figures. They're just different ways of writing them. Any questions about multiplication, division, addition, subtraction, or numbers of significant figures? By themselves, they're not too bad. We also get to use them together. And so this is where you remember your dear Aunt Sally. She's coming back. So the dear Aunt Sally thing, PEMDAS, please excuse my dear Aunt Sally, or just PEMDAS. We get to use the rules of PEMDAS and take this one step at a time. There's no need to rush. So we're going to do the steps in parentheses first. We're not going to worry about exponents here. So whatever we have in parentheses, we'll do that first. Then we get to figure out significant figures in our intermediate answer. This is a great place to put the little line under to keep track of our significant figures as well as keep track of our decimal places. And then we can do whatever steps remain. The MD does not stand for medical doctor. It stands for multiplication division. These happen at the same time. And then our last step is add, subtract. Those also happen at the same time. So a little bit of math reminder. Now on to what is probably more helpful, doing some actual calculations. We want to do each of these calculations with the correct number of significant figures. The things with units are our measurements. The twos that I've included here the twos here are exact. This just applies to this. We're treating the twos as exact numbers. They were part of a formula, let's say. All right, so our first example, letter A. We've got 1.008 grams in parentheses. It's in parentheses just to show you the 2 is multiplying by the 1.008. I could have also just written multiplied by. And we're also adding 15.99 grams. We don't have anything happening inside of the parentheses. It's just there to protect our number, our measurement. So we don't do parentheses. we skip exponents. We don't have exponents. Then we do multiplication division. So our first step, we're going to do multiplication. So 2.016 grams. The numbers that went into it are the 2, which I've told you are exact, and the 1.008 that has 4 significant figures. Since the other one's exact, we're going to have 4 significant figures in our intermediate answer, the 2.016. So we're maintaining 4 significant figures. Okay, intermediate step done. Next step, addition, subtraction. We get to add the 15.99 grams. Now we've switched from caring about significant figures to caring about, or not caring about, but considering decimal places. 15.99, 2 decimal places, 2.016, 3 decimal places, because we've got 3 significant figures after the decimal. So 2 is the smaller of those numbers. We'll have 2 decimal places in whatever our answer there is. Calculator says 18.006. We're going to round that for 2 decimal places. 0 under the second, or sorry, line under the second 0. Arrow at the 6, that's what we're using to round. And turn that into 18.01. What am I forgetting? Lots of things. In this case, grams. We need our units. Questions about that first one? All right, second one. Similar sort of problem. We have 2 times 35.45. We also have some addition. We're adding 137.3. What are we doing as our first step for problem B? Yeah, we're multiplying the 2 and the 35.45. Again, we said that 2's are exact in this case. So 35.45. We've got 4 significant figures. Our intermediate answer will also have 4 significant figures. Brango Burr, no, go away, Siri. Brango Burr, say 70.90 seconds. So that's our intermediate answer, and then we can add to that 137.3 seconds. Calculator says 208.2 seconds. Is that the correct answer to report? Yes, that's the correct number to report. 2 decimal places, 1 decimal place. We want to give our answer with 1 decimal place. Our calculator conveniently dropped the 0 that would have shown up after that 2 if we had done it manually. All right, last one. C in italics for some reason. Same sort of setup. Our first step, we're doing 118.7 grams divided by 2. we'll put that in the calculator. Calculator says 59.35, and we know that it's grams. Just checking our significant figures, we had 4 in 118.7 grams, and conveniently 4 still with our 59.35 grams. So we've maintained our 4 significant figures. And what do we care about when we switch to addition subtraction? Decimal places. So minus 35.5. We have 2 decimal places and 1 decimal place, the smaller of the 2 being 1 decimal place. Calculator says 23.85, and we know that it's grams. Our 1 decimal place is the 8. Arrow at the 5 to let us know that that's what we're looking at to round. So this becomes 23.9 grams. Questions about significant figures? It's normal to occasionally, regularly even, forget how significant figures work. That's okay. You're welcome to ask during lab. That's all we have for today. See you in lab.